Okay, everybody, how's it going? Today we're going to be looking at the Chapter 12 practice test. This is the first video of the series on this Chapter 12 practice test, which has to do with all of the other stuff about linear regression. So we're talking about transformations to achieve linearity. And we're also going to be talking a bit about confidence intervals and hypothesis tests for the slope of a regression line, which happens to be what this first question is all about. So we have a list of properties here about which one of these is not going to be a condition that has to be satisfied in order to perform a inference about a slope of a least squares regression line. So if you will remember, we're talking about linear here. These are the conditions for a t test or a t interval for the slope of a regression line. The first property here is linear scatterplot, which also means that there's no pattern in the residuals. So let's see if that helps us see where that is for any of these. Let's see, this first one is about standard deviation. That's not really about a linear scatterplot. The data has to come from a simple random sample. We'll get to that later. Sample size has to exceed 30. That sounds like we're talking about a CLT. There is a straight line such that for each value x, the mean mu of the corresponding population values of y lie on that straight line. So that's a little bit about things actually being a scatter plot, being linear. That one tells us that the true shape of the relationship is linear, which again, that kind of jibes with L, linear scatter plot. I stands for independent, which for us has to do with the 10% condition. Considering that this is a random sample, we need to make sure that we are not sampling so much that it changes the independence. But there's nothing here that has anything to do with independence. So we'll skip that and go to N. N stands for normal residuals. And what that means is that if we plotted the residuals with either a dot plot or a histogram, there's not going to be a strong skew or outliers. And there's actually nothing here about that one. So we're going to move on to E. E stands for equal standard deviation, which basically means that if you are, or the test for this is to look at the residual plot, and you shouldn't see a triangle pattern. So there's a few of here. There are actually, I saw two of these that are similar to this one. And the first one is letter A. And letter A says that the standard deviation sigma is the same for any given value of x. So that's kind of what we're saying here with equal standard deviation. The standard deviation for any value of x is always the same. Also, if you take a look at letter E, we see that for each value of x, a population of y values is normally distributed. And if you think about the y values being normally distributed, well, they're not going to hit the line exactly, but they could be above the line and below the line, which means that the residuals, which is the distance between the actual y values and the y values on the line, well, those need to be normally distributed as well. Those are the residuals being normally distributed, so that is also equal standard deviations. So taken together, letters A and E, those are both about the equal standard deviation condition. So both of those are going to be true. The R condition, like always, is random sample, and we can see that letter B is about that random sample or random experiment. So the only one here that doesn't actually fit is letter C, and you probably didn't even need to go through all of these, the other four, in order to arrive at C as the correct answer here, which would be an incorrect condition, because there is no such thing as a central limit theorem here. That is, there's no central limit theorem when we're talking about a least squares regression line. So since there's no CLT for the inference about a slope, this is not a condition for a least squares regression line inference procedure. Let's take a look at this next scatter plot. This looks like a pattern. You could argue about this pattern being a exponential growth or just power growth, maybe a second degree growth. That's the first thing I'd want to say here. This isn't, you'll notice the curved pattern, of course. This definitely is not a linear pattern. So there is some curve here. This question says, students in a statistics class drew circles of varying diameters and counted how many Cheerios could be placed inside the circle. That's a very interesting one. I think that has to do with area. The scatter plot shows the results, and students wanted to determine an appropriate equation for the relationship between the diameter of the number of Cheerios, between diameter and the number of Cheerios. The students decide to transform the data to make it appear more linear before computing a least squares regression line, which is a great idea. Now, for these ones, which of the following transformations should we try? This first one, plot the square root of the number of Cheerios against the diameter. Well, that sounds like a good idea because we are talking about area here. I mean, if we're trying to find out how many Cheerios fit inside of a circle, we're really interested in the area of the circle. And so since the square root is the inverse operation for a square relationship, that's a pretty good idea. Number two, plot the cube of the number of Cheerios against the diameter. Well, cubing the number of Cheerios will only make the y-coordinates more extreme. And if we make the y-coordinates, the number of Cheerios, more extreme, we're basically looking at a curve that would be even worse than what we already see. So that's probably not a good idea to use a cube here. This next one says to plot the log of the number of Cheerios against the log of the diameter. So this is going to create a power regression, which is like the shape of y equals x squared, or y equals x cubed, or y equals x to the fourth power. And this is a pretty good idea since, again, we're looking at the square relationship of area. Now, I actually made a little bit of mistake here for this one right here. It says the cubic relationship. Basically, what you're going to do is you're going to take the y coordinate and you're going to cube it. So the real transformation here is y equals y cubed. Yeah, and for the same reason, that's not going to work also. Number four, plot the number of Cheerios against the log of the diameter. This one looks like it is an exponential transformation, but it's actually kind of backwards because when you look at this, the number of Cheerios is the dependent variable, so the y-coordinate, and then the diameter is the independent variable, or the x-coordinate. So what you're really plotting here is log of x versus y. The actual exponential transformation is the x-coordinate versus the log of the y-coordinate. So this takes the log and puts it in the incorrect place. So the only two that work here are numbers 1 and 3. And then the last problem we're going to do in this video, inference about the slope beta 1 of a least squares regression line is based on which of the following distributions. And it's kind of hard not to really go here, but we know it's a t-distribution. So definitely not a normal distribution. Definitely not a chi-square distribution. Not a standard normal distribution either. And the one that's wrong, or these two are only different because one has an n-2 degree of freedom and one has an n-1 degree of freedom. So this run over here, this is our correct response t-distribution with n-2 degrees of freedom. So that's going to do it here for this first video on Chapter 12. We'll see you on the next one for the Chapter 12 practice test.